In this video, I'd like to talk about the math question of the day for January 24th, 2023. And for this problem, we need to draw a picture or a graph of this quadratic equation, the second degree polynomial, which will essentially create a picture of a parabola, something that looks like either an upside down or a right side up U. And we also need to identify the key features, the vertex and the x and y intercepts. So to answer a question like this, you do need to have a deep understanding of quadratics and how to graph in general. So at this point, go ahead and pause the video, see if you can figure this out, spend at least a couple minutes going through this, and when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted this problem, we can go through the solution together. And as always, if you have a suggestion for a problem of the day, please feel free to leave that in the comments. So let's start by just rewriting this equation. We have x squared minus 3x plus 4. This is all equal to y. And when graphing quadratics, there are a few strategies we could employ here. The simplest one is to construct a table. Pick different values of x and figure out what their y values are and then plot those points. But with quadratics, that can be a little bit tedious since it's better if you understand the patterns. And remember that it will create a parabola, and this parabola has a vertex, a lowest point, or it could be the reverse of that, it could be the highest point. And it also has symmetry, namely about the x value of our vertex. It's a mirror image on either side. And let's say we're graphing this on the coordinate plane. The zeros, the x-intercepts, will be the same distance away from the vertex. So these quadratics have quite a bit of symmetry, and we can use that to our advantage. And one approach we could take is to try to factor this into a product of two binomials, where we have two terms in each of these. And each of these would be x, since if we multiply this out, we would get x squared. But these number terms right here, they would have to multiply to 4 and add to -3. But that is not going to be possible. If we look at all the combinations for positive 4 and what multiplies to 4, namely 2 and 2, 1 and 4, or -2 and -2, and -1 and -4, none of those add to -3, meaning that we can't factor this in any simple way. So that's not the approach we're going to take here. What we're going to do instead is a process called completing the square. Essentially, we will transform this equation into its vertex form, namely that y is equal to some coefficient a multiplied by x minus h squared plus k, where our vertex v is at the coordinate h comma k. So this is our strategy. We want to transform it to this vertex form. And again, to do that, we need to use a process called completing the square. And we can rewrite this where we leave a space after the x term. Since with completing the square, we will add a certain number here, and we will be able to factor this into a perfect square, some expression squared like we have here. But once we add that number, then we will again subtract it so that it cancels out and we don't actually change the equation. Now, to figure out what number to add so that we can transform this to a perfect square, we can look at the pattern for a perfect square actually multiplied out. If we have, let's say, x plus a squared, and we multiply this out using distribution x plus a times by x plus a, what we will find is that we get x squared plus 2ax plus a squared. So we essentially have this right here, x squared minus 3x. This is our x squared plus 2a times by x. And we just need to figure out what we need to add here so that we can essentially go backwards and transform this into some binomial squared. And to figure that out, we just need to figure out what a is and match it up with our -3 here. We can see that twice a, the coefficient on x, in this case would be -3. meaning that a is minus 3 over 2. And notice that once we add our a squared value and factor this, we'll get x plus a, meaning that this right here will eventually simplify to x minus 3 over 2 squared. But to get there, we need to add a squared. We will be squaring this number. So we are adding minus 3 over 2 times minus 3 over 2, which would be 9 over 4. But we can't just add a number. We also will have to subtract it so that it cancels out. So this right here is what will simplify to x minus 3 over 2 squared. And you can test this by just rewriting this twice and then multiplying it out. But when you do test it, you will see that these two are equivalent to each other. So we just need to simplify this part right here. We have 4 minus 9 fourths. 4 is really just 16 over 4 minus 9 over 4. So we get plus 7 fourths. And comparing it to our vertex form, the vertex is at an x value, which makes this expression 0. And the x value that makes this 0 would be positive 3 over 2. And when we plug in 3 over 2 here, this is 0, and y is just equal to this number right here, this 7 over 4. And notice that is exactly what we see here when we look at the general form for our quadratic in its vertex form. So we call this the vertex form of a quadratic equation. And we just found the vertex. It's at 3 over 2, comma 7 fourths. So let's start making a picture now. Let me scroll a little bit to the left here, and I'll paste in a coordinate plane. And for this equation, we know its vertex is at 3 halves, or 1.5, and 7 fourths, which is 1.75. So if we go 1.5 to the right and up to 1.75, that is our vertex. And we expect it to open up because the coefficient on x squared is positive. So it should go upward like that, meaning that it won't have x-intercepts. In fact, we can test this because the x-intercepts just come when y is equal to 0. We can set this equation equal to 0 and solve it so that we have 0 is x minus 3 halves squared plus 7 fourths. We will subtract 7 fourths on each side, so minus 7 fourths is equal to this squared expression, but that should throw up a red flag. When something is squared, it is always bigger than or equal to 0. So this expression can never be negative, meaning that there are no real solutions to this. In fact, if we wanted to solve this, we would get imaginary solutions or complex solutions, and that just means that the graph doesn't cross the x-axis. So we can ignore that. We can say that we have no real zeros. And since we don't have x-intercepts, we can now look at the y-intercepts. And remember, the y-intercept just comes when x is equal to 0. So if we plug in 0 to our equation, and when it's written in standard form, it's probably easiest to do that. So when, let me use a different color, when x is 0, y would just be, this is supposed to be a positive right there, 0 minus 0 plus 4. Or simply, this goes through the y-axis at 0, 4. We can plot that point that is right here. And remember that with these quadratics that they're symmetric about the vertex, meaning that if we draw in this line of symmetry, this is when x is 3 halves. We have a mirror image on either side of this. And it looks like when we go left of the vertex, 3 halves or 1.5 units, that we get a y value of 4. So if we go right 3.5 units, we will also get a y value of 4. And you can see the symmetry there. So at 3, 4, we also have a point, and we could of course test this. If we plug in 3, we get 9 minus 9 plus 4, which is just 4. So at this point, we've identified the vertex, we've identified the intercepts. It just has the y-intercept, there is no x-intercept. And this right here is a fairly accurate picture of this equation, y is equal to x squared minus 3x plus 4.